Now it looks like we must be looking not down on the plane, not from the north. This must be looking up from the southern half of the galaxy. Now we've got everything rotating counterclockwise here. But now we're looking at deviations from perfectly circular orbit. So let's make a deviation. Let's just arbitrarily say we'll push an object away from the center of the galaxy up here. Just displace it up here, further away than the guiding center wants to be. So what happens here, the angular momentum is conserved for this object. R times V is conserved. Well, since I just made R bigger, that means the orbital velocity in the phi direction here is going to be smaller. So compared to the guiding center, the displaced star up here is going to start lagging behind. See, everything's trying to go counterclockwise, but this thing is going to start falling behind the guiding center, so it's going to move clockwise. It's a retrograde epicycle. By the way, I think that's a difference from Ptolemy. He had prograde epicycles. Because they are further away from the guiding center, we need to remember the guiding center is determined by basically two forces. One is the force of gravity, pulling you towards the center. That's roughly, let's say, 1 over r squared force. But then there's the so-called centrifugal barrier, just v squared over r. And for a typical galaxy, v squared over r, the centrifugal barrier, weakens not as 1 over r squared, but 1 over r cubed. So the centrifugal barrier force here, they were perfectly in equilibrium. These two forces were exactly equal. This force equal to this force right here. But what happens when we displace to larger r? Centrifugal barrier force, that's the force pushing you out in a rotating frame, has now become smaller. The gravity force wins. So the extra gravity out here, or the smaller centrifugal force, wants to what? Pull you back towards the radius of the guiding center where you were. It's a restoring force, wants to pull you back to your correct circular radius. You'll be lagging behind, but you'll gradually be pulled back to the guiding center radius, and then you'll overshoot. And then, of course, everything, and now you're at a smaller radius than the guiding center, and everything's the opposite of what I said before. Now you're going faster than the guiding center, so you're overtaking it. You get out to a minimum distance away from the galactic center, and then you find that actually the centrifugal force is winning. It's beating the gravitational force, and so you're in effect pushed back like this. In every case, as soon as you get away from the guiding center, you're pushed back towards the guiding center. You can approximate these deviations from the equilibrium position as a linear restoring force. We can expect to see simple harmonic oscillation around the equilibrium. This is like a universal theme of motion. See, it's not just for gravity. These stars are going to execute these retrograde epicyclic ellipses. This is really just the definition of what a circular orbit is. V squared over r is equal to the first derivative, the first radial derivative of the gravitational potential. That's how you would figure out where the guiding center is. It's just basically where everything goes on circular motions and has no need of epicycles. But let's put in an epicycle. So now we'll call the deviations in the radius x. When x is positive, that means your object of interest. This could be the sun, by the way. The sun executes epicycles about its guiding center. It defines an effective potential, which is basically the gravitational potential plus a centrifugal barrier. It's in a rotating frame. In a rotating frame, you have this centrifugal barrier. I don't want to. X double dot is equal to minus x times the second derivative of this potential gradient. If you define that as the simple harmonic oscillation frequency squared, you get the formula for a simple harmonic oscillator. X double dot is equal to minus a constant squared times x. The guiding center is where there's a minimum in the effective potential. That's going to show energy, and then this is going to be radius, energy per unit mass, and this is going to be distance away from the galactic center. Determining the circular velocity is a balance between these two terms. But typical gravitational potential, it might go down very negative close to the center of the galaxy could be minus infinity there. And then it goes up. It might be logarithmic. But then I have to add on to this the centrifugal barrier, which is basically v squared over r. So that's positive. So let me draw that one coming to v squared over r. What does that look like? 1 over r, like that. So it looks like that. All right, so let's write what that is. That's the centrifugal barrier, which is v squared over r. The effective potential, because I add these two together. This term wins in the center. All right. Then they bottom out here at a minimum, and then this thing wins, and it looks like that. So this here is phi effective. The guiding center here wants to be at the minimum of this, and r changes back and forth depending how big a kick. Let's give it a sort of a medium kick. So we'll kick it up to here, and it goes pulled back to there, and it gets pulled back to there, gets pulled back to there, and so on, back and forth here like this. This could be approximated by what mathematical form? A parabola. Parabolic energy means linear restoring force, because that's just the first derivative of the parabola. Linear restoring force, the further away you get from equilibrium, the harder it pulls back, and that means it's simple harmonic oscillation, back and forth, back and forth. It's going to tell you what the answer is here. There's like a few lines of algebra here. I just have to know what omega is, which we know, and then I have to know, this is a little bit complicated, the radial derivative, d by dr, of omega squared. This is obviously related to the shear. And the sum of these two things is going to basically give me a restoring force to pull me back towards the guiding center. Two simple examples which will maybe demystify this a little bit and make you feel more comfortable with the formula. How about example number 1? This is not realistic except maybe in the central parts of galaxies. What if the galaxy was rotating like a merry-go-round and solid body rotation, so omega is a constant at all radii? They all go around with the same number of radians per year. And so there'd be no radial derivative at all, no radial dependence of omega squared. So this term, the first term here, would be in that case what? 0. The angular frequency, radians per second, is kappa is equal to twice the orbital angular frequency, also measured in radians per second. What if we had all of the mass in the Milky Way galaxy concentrated down to a single point of mass m at the center, like the Kepler problem? That's like the solar system, where all the mass is just the mass of the sun. Well, V would be square root of gm over r. Dividing that by r would give omega is the square root of gm divided by r to the 3/2. Omega squared is gm over r cubed. And what's the derivative with respect to radius of gm over r cubed? Minus 3 gm over r to the 4th, which happens to equal minus 3 omega squared. Minus 3 omega squared plus 4 omega squared equals omega squared. So the square root of that is kappa. Kappa is exactly equal to omega. There's the galactic center. So that is the guiding center motion. So let's start at the top here, and let's suppose that we started, like in my example, with the maximum excursion of our epicycle away. So I'll put us up there. So we're starting here. That's us. We're away. All right, but there is a linear restoring force pulling us back in. So after we've gone a quarter of the way around, then we've gone from our maximum distance away to how far? We'll be at 0 at that point. We'll be passing through the guiding center. After we've gone half a cycle through, remember this is a cosine oscillation, it started at +1. Here, it's at 0. Now, let's go down to 180 degrees. Which way are we going to be there? Remember, this is half an oscillation. We started out all the way out to large radius. After half a cycle, where are we? All the way in. And by the time we get to 3/4 of a cycle, where are we going to be here? Passing back through the guiding center, connect. all of these points together. We hit the guiding center here, and now we're on the inside of the guiding center. As we get closer and closer, then the repulsion force, the centrifugal gravity, pushes us back away. We get out like that, and further and further out until we end up like this. This is an epicycle approximation, which is a pretty good approximation, is very close to an ellipse with the galactic center at one focus, which is exactly the correct answer for Mr. Kepler. So, because we start out past the guiding center, and we must conserve angular momentum, we're temporarily at a smaller v phi. So the guiding center is going to leave us behind a little bit temporarily. So we'll lag behind. Our epicycle is actually going to go retrograde like that. Actually, it goes like this, right? It's an ellipse like that. See, so I just picked a very beautiful, simple case where there's one epicycle for one orbit. It's perfect. An integer number of epicycles is completed in an integer number of orbits. It returns to the same place it started, doesn't it?
Yeah.
So let's now look at the second case, which is not obvious, and I bet you haven't seen this one before. This is the opposite of having all of the mass concentrated in a point at the center. So the first case I did, the Kepler case, is like the most possibly concentrated mass distribution you could possibly have. Now I'm going to have no concentration at all. I'm going to have the mass totally uniformly spread out. 2 epicyclic oscillations for each time around. This is another case where it is an integer relation, a 2-to-1 relation, and so this means that it is going to come back to the same place. In the solid body case, I'm going to just do the same thing. I'm going to start us off outside at my maximum displacement up here. So by the time we get down to 3 o'clock, that's only a quarter way around the orbit, but that's halfway around the epicycle. So if you start at +1 and you go pi, that's halfway in. Where is the epicycle? Here at 3 o'clock. It's all the way maximally inward. And now it gets down to 6 o'clock here, and it's already completed an entire epicycle. So where would it be? All the way back out again. See, maximum R. X is positive there. And then, of course, it's going to execute another epicycle in the second half of the orbit. So it'll be crossing over here. It'll be all the way maximally in here. It's 3/4 the way through the orbit. And then it'll cross back over here. I am ready to connect this. Go into 0, minimum, out, maximum, min. God, this is horrible. What have I just drawn here? It's a darn good ellipse. And that is the correct answer. No, this is not Kepler's law. Where's the center of the galaxy in this ellipse? It's in the center of the ellipse, not at one focus. What if there's not an integer number of epicycles during one orbit or during an integer number of orbits? What if there's not an integral ratio between kappa and omega? Then all this pretty stuff is going to be messy. It's not going to.
It doesn't return to its starting point?
It will not return in general to its starting point after it goes once around its orbit. It'll be somewhere else. What if we took a realistic case now where we had a flat rotation curve? So that means omega goes as 1/r. And so let's plug that in then. If omega is 1/r, then I can certainly take the square of it, which is 1/r squared. Let's see. Here it is. So that's 1/r squared. I take the derivative of it with respect to r, and I get 1/r cubed. Then 1/r cubed times 1/r squared. This term is just v squared over r squared again. It is a minus, though. Minus 2 omega squared here, plus 4 omega squared here. This whole thing in parentheses, this is correct, comes out to 2 omega squared. Everybody can take the square root of that. Oops. Not really, because the square root of 2 omega squared is omega times the square root of 2, an irrational number. In one trip around, in a realistic flat rotation curve, the sun or the epicycle object will have completed an irrational number, more than one epicycle, less than 2. Those were the 2 extreme cases, right? If we had all the mass concentrated at the center, or if we had the mass not concentrated at all, we'd either get 1 or 2 epicycles in one trip around. We ended up somewhere in between, where the mass is somewhat spread out. It's not uniform. Actually, it's a 1 over r squared density distribution. That's what gives you a flat rotation curve. Then we're stuck in limbo here, completing square root of 2 epicycles every time we go around. So we're never going to come back to the same place. Now, this is an actual drawing of it. Okay, this was not for square root of 2. It was for 1.3, but you see the same basic issue. There's the guiding center, is the dashed circle there. It's a perfect circle centered on the galactic center there. We start out, I'm sorry, we're going in the opposite direction. We cross in the guiding center. We get all the way into our closest approach. Then we get all the way back out to our furthest distance away. Oops, we've completed one epicycle, but we're over here now. We still have, another like third of the orbit to go here. Oh, bummer. So now we start falling back in. We cross over, and by the time we've completed one orbit, we're down here. We're a little bit inside instead of being outside. We're not even all the way inside. We're neither in, we're just passing a sort of a random arbitrary place. Then we go further in here, and this is never going to connect up here. I could just keep on drawing this thing. The second time around, we're here. So we haven't connected with either of the first two trips. We're at a different place. And then, so now I go around a third time here, and I'm getting bored with this. You can see after a third time, this curve is never exactly going to close itself back up, although eventually it'll get pretty close. But if you went around dozens of times, what would you eventually see this line do? It would just be a solid scribble everywhere from the maximum point you could go here. That's where you're at the turning point in that effective potential. That's as far out as you can go, all the way down to the inner turning point, whereas you're closest in. It would just be a big gray band. Here's some more algebra that I just saved you from. You shouldn't be surprised to know that if you wanted to know what the epicyclic frequency was locally around the solar neighborhood, that is a naught here, then here's a formula for kappa naught squared, purely in terms of the 2 Oort constants. B is negative, kappa squared is positive, and kappa is the square root of that, which is a real number. And we plugged in the actual numbers here. If you use the best estimates that people put in for omega naught, use the best estimate for what B is, then you get pretty much what I said. Kappa is a somewhat higher frequency. Now, if you look at this pretty carefully, if I took this 1.414 times the 27, square root of 2 times that, it'd be pretty close to 37. Not exactly, though. Actually, that previous diagram that I showed is probably more precise. The kappa is about 1.3 times omega. So we're close to a flat rotation curve in the local solar neighborhood, but not exactly a flat rotation curve, but close. I made a little bit of a cheat there because actually we're currently moving in. So we're moving forward. So we're not at exactly RG, but close enough. If you have orbits of stars that generally look like this, how could you ever have a bunch of stars' orbits that would make a pattern in a galaxy such as we sometimes see? I'll just give you a very simple case. Sometimes galaxies have bar-like extensions, sort of an elliptical looking thing where there's a bunch of stars on it, which of course is a deviation from purely azimuthal symmetry. Another deviation that I'll show you pictures of this that you've seen in many spirals, that's why they're called spirals, is you often see spiral arms, which are also arms of stars. It's not just the gas there. So there are concentrations of stars, there are more of them, clustered along these spiral arms. Now, how could you have any pattern that would last for more than one turn around the galaxy? Because the stars would move away from the radius. Say you set them all beautifully. Got the stars all right here. Makes a beautiful little spiral pattern. Makes a beautiful little bar pattern. I just got it just right. Put all the stars at the right places. Well, they won't stay in your bloody pattern after you just let them go around once, because they came back to the wrong radius. The same stars, because they generally orbit like this, cannot stay in your beautiful pattern. So I cannot get all of the stars to physically be in a pattern that will last, for some time, for a number of turns. But I could set them up in a pattern and then let the pattern move at a different speed from the orbits of individual stars. A pattern speed, which would not be the same as the individual orbital speeds of individual stars. The pattern would move around, and different stars would enter the pattern. If they're on faster orbits than the pattern, they'll catch up to the pattern, they'll move into the pattern, and then they'll leave the pattern, exiting, leaving it behind. Or if the star is moving slower than the pattern might catch up to the star. It's a wave. It's exactly a wave. It's called a density wave. You could have an explanation for this observed fact that the galaxies have these patterns. They have these clear deviations. They're not all just washed out and uniformly axisymmetric. The spiral galaxies do not in general look like that. So we need some way that a pattern can last for more than just one circuit around. And so we've got to have density waves to explain what you actually see in galaxies. So how would you do that? There's a lot going on in this diagram. I've got a pretty realistic kind of flat rotation curve. Suppose that I put in a very slow pattern. In other words, I'm going to jump into a frame that rotates with the galaxy at a rotation omega p. So I'm going to give myself a little bit of a rotation, which we call omega p. I'm moving into a rotating frame, and now I'm going to watch the stars. If I choose the pattern cleverly, then I might be able to choose the pattern so that in my rotating frame, this orbit closes back up on itself after a certain number of epicycles. Could you actually do that for a pattern that extends over different radii? Rather difficult to do, unless you look for a particular special pattern, which is a two-arm spiral pattern. What's a two-arm spiral? It means that as you go around an azimuth, there are two maxima and two minima. Typical epicycle completes two epicycles in one rotation of the galaxy in this rotating frame. And it was noticed a long time ago, you actually have fairly wide range of radius if you plot omega minus kappa over 2. Don't worry about omega plus kappa over 2. If you go at that pattern speed, there'll be a fairly wide range of the galaxy where a two-arm pattern would sustain itself. The stars would appear at this pattern to have complete orbits, closed orbits. So this could actually work until you get to inner parts. This point where omega minus kappa over 2 drops below the pattern speed is called the inner Lindblad resonance. And that's actually pretty and cleverly named point, because it really is a resonance, which is going to help the spiral pattern keep going. I'm now in a rotating frame. All of these are ellipses, and I cleverly line them up so that the major axes of all these ellipses are all horizontal like this. That's a pretty good approximation of a bar pattern. This is not a very impressive bar, but at least it's a deviation from a spherical symmetry, and it has a twofold asymmetry in it, so that we'll call that a bar. This pattern could last a long time. It's just that the bar would drift with respect to the motions of the actual stars. The actual stars won't stay together, but the pattern persists. And it's really beautifully shown here where we have a bunch of stars on ellipses. Remember, an ellipse is when you complete 2 epicycles, 2 radial oscillations for every 1 orbital oscillation. Instead of having all the ellipses lined up together, I twisted the ellipses like this to make a beautiful 2-arm spiral pattern. Every time the star comes back, this pattern will still be there. You can see that there's a very strong concentration of star orbits. They're all getting really close to each other along this line and along this line. Now, if we included gas in this picture, the gas clouds are, are big, squishy interstellar gas clouds. They're going to actually collide with each other at high velocities and produce shock waves. The stars are so small, they don't actually collide. So all of these are possible, that you could have long-lived patterns like this in a galaxy with a realistic rotation curve, like I showed you here. Let's say that the rotation is counterclockwise here. You could make a 2-arm spiral where the arms are leading. See, the rotation is in this sense, counterclockwise. That would be called leading spiral arms. Or I could do the same thing with trailing spiral arms. In this is a simple, it's called a kinematic picture, this simplistic picture of picking a pattern speed to use the epicycles of the galaxy to have a sustained spiral density wave. It could be either a leading or a trailing arm. Either one is allowed. But in real galaxies, in real spirals, energy is dissipated from interstellar gas clouds when they experience shocks passing through this wave, and you never see leading 2-arm spirals, so far as I know. It's tricky because you have to know which is the front and which is the back side of the galaxy. But every case that I know, the spiral pattern, when there is a 2-arm spiral pattern, it's not always a 2-arm spiral pattern, but it is the most common, is always trailing arms. So all of those things that I just said, the fact that you see 2-arm spiral patterns, the fact that you see bars, the fact that trailing spirals are preferred, all of these things are considered to be confirmation point of the spiral density wave theory of galaxies.